Hi there. In this tutorial, you and I are going to take a brand new open source language model, get it running locally on a single graphics card, and double its speed using a clever trick called multi-token prediction. We will start with what the model is, then jump straight into the 3 use cases I built, then look at the engine choice, including one path that did not work, and finally, for the curious, an advanced deep dive into the full installation. Let's go. First, let's talk about the model itself in the most non-technical way I can manage. No jargon, no math, just the high-level picture. Qwopus 3.6 is a language model with 27 billion parameters. Think of those parameters as little dials inside the model's brain that got tuned during training. It was built on top of the Qwen 3.6 family, then fine-tuned by an independent author for tasks like writing code, solving math problems, and answering DevOps questions. You download it as a single GGUF file, which is just a portable format that any laptop or workstation can read. The 4-bit version we will use is about 16 gigabytes on disk. Best of all, it ships with an patched 2.0 license, so you're free to use it however you like, including in commercial products. Here is the catch with running a big model on a single graphics card. The model writes its answer one token at a time, where a token is roughly a word or part of a word. Each new token has to wait for the previous one to finish, like cars on a single-lane road. On a single RTX 4090, that limit is around 44 tokens per second. That sounds fast on paper, but when the model is writing a long answer, you absolutely feel the lag between sentences. And that is where multi-token prediction, or MTP, comes in. The idea is surprisingly simple. Instead of asking the model what the next single token is, MTP asks it to guess 2 or 3 tokens ahead in the same forward pass. Then, in that same pass, the model verifies its own guesses. When the guesses are correct, and they usually are, you basically get 2 or 3 tokens for the cost of 1. The technique was first introduced by DeepSeek's V3 model and has become mainstream throughout 2020, with the Qwen family adopting it for its 3.5 and 3.6 lineups. Let's put numbers on it. On our hardware, the same Qwopus model without MTP generates about 44 tokens a second. Turn MTP on, change nothing else, and the average climbs to 87 tokens a second. That is a 1.98 times speedup. Importantly, you don't sacrifice any quality. The verifier guarantees the output is identical to what you would have gotten the slow way. And for math reasoning, where the model's chain of thought is very predictable, the speedup jumps to 2.2 times. Before we get to how this was installed, let's see what the thing can actually do. I picked 3 real use cases that represent very different workloads: code generation, DevOps shell scripting, and step-by-step math reasoning. Use case 1 is a coding question. I asked the model to write a Python function that computes the nth Fibonacci number using memoization. It correctly reasoned that functools.ulraru_catchy is the most Pythonic approach, added a guard against negative input, and produced a clean, idiomatic snippet. The MTP-enabled generation speed for this answer was 82.8 tokens per second, almost 2 times what we'd get without MTP, perfect for in-editor code completion. Use case 2 is the kind of one-off shell scripting you do every other Tuesday. I asked, write me a bash one-liner that finds the 5 largest files in /var/log and prints their sizes in megabytes. The model thought through 3 different approaches, using DU, using else with sort, and an AUK variant, and then committed to the tightest one-liner, plus a 4-bullet explanation. Speed for this one was 81.6 tokens per second, a 1.85 times speedup. Use case 3 is the one where NTP really stretches its legs. Classic probability question. A bag has 4 red and 6 blue marbles. You pull 2 without putting them back. What's the chance both are blue? The model walked through the answer step by step, calculating each conditional probability, then verified itself with a combinatorial sanity check. The answer is 1/3. And here is the punchline. At 97.8 tokens per second, this was our fastest generation of the entire benchmark, a 2.21 times speedup. Math reasoning has highly predictable tokens, which is exactly what MTP is best at. Now let's pull all three use cases together and see exactly what MTP buys us in tokens per second, side by side with the baseline. Here is the picture. The blue bars show baseline speed without MTP, flat at around 44 tokens per second, regardless of task. The green bars show MTP with 2 draft tokens, a clean jump up to around 82. The orange bars show MTP with 3 draft tokens, peaking at 98 on the math task. Average speedup with the best setting is 1.98 times. Same model, same hardware, same answer, almost exactly twice as fast. If you just want the recipe, here it is. Use the Llama server, which exposes an OpenAI-compatible API on port 8080. So anything that talks to OpenAI, LangChain, small agents, the OpenAI Python SDK, can drive this model with a single base URL change. The flags that matter most are --spec-type draft MTP and --spec draft max3. Also quantize the KV catch to key 8_0. That halves your memory use with no measurable quality drop at sensible context lengths. Bind on 0.0.0.0 so your agent frameworks on other machines can reach it too. A fair question, because Llama was already installed on the test box. Before building anything from source, the honest move is to try the simpler path first. So let me show you what happened when I tried it, and why I ended up back on llama.cpp anyway. Step 1 of the Llama attempt. The machine already had Llama version 0.24, the latest stable release, with 19 models in its library. I wrote a 5-line model file pointing at the same GGUF we already downloaded, and ran llama create. It succeeded in about a second, because Llama just hard-linked the existing blob, no re-download. Inspecting the model shows the architecture is Qwen 35, the dense Qwen 3.3.336 family. So far, everything looks completely healthy. Step 2, and here is where the wheels come off. The moment you actually call the generate endpoint, Llama throws an error instead of a response. The error message is very specific. Qwen 3 next. Layer 64, missing engine QKV and gate projections. 0 tokens generated. Llama bails out before even loading the weights. To confirm this is MTP specific and not a broken runtime, I ran the plain non-MTP Qwen 3.5.ab from the same library on the same API. It ran at 332 tokens per second, clean exit. So the runtime works fine. It is the MTP augmented layer 64 that breaks it. Here is the root cause. Llama's MTP support, added by pull request 15980, was designed for Gemma 4. Gemma 4 keeps its draft model in a separate safe tensors file, pointed at via a new drafty keyword in the model file. The Qwen 3.5 and 3.6 family takes the opposite approach. The draft heads are baked directly into layer 64 of the same GGUF. When Llama's Qwen 3 next loader walks that layer expecting standard attention projections, it finds MTP draft head weights instead and bails out. The fix has to come from Llama upstream. A future minor release will likely add Qwen 3 next MTP support. Until then, llama.cpp is the only engine that can actually use this GGUF. So this is the path that actually works. 6 steps end-to-end. Clone the upstream llama.cpp main branch. MTP support landed there in May 2026 and has been stable since. Configure SMAKE with the QDA backend enabled and the RTX 4090's compute capability, 89, pinned in. Compile in parallel, which uses every core on your CPU. Download the 4-bit Q4_K_M version of the GGUF, 16.8 GB, to a data disk with room to spare. Then run Llama server with the magic flags, --spec-type draft MTP and --spec draft max3. The MTP draft heads embedded in layer 64 do their job, The verifier confirms each speculated token, and you end up with an OpenAI-compatible API on port 8080, generating about 2 times faster than the same model without MTP. Alright, heads up. From here on, it gets technical. This is the advanced part of the tutorial. If you just wanted the recipe, you already have it. If you want to reproduce the whole thing on your own machine, the next handful of slides cover every step I took, plus every wall I hit along the way. Here is the setup. We are on Qwopus 2204, which is just Ubuntu under the hood with a single NVIDIA RTX 4090 graphics card. That card has 24 gigabytes of VRAM, which is the magic number. It is just barely enough to hold a 4-bit Qwopus model and leave room for context. The QDA toolkit is version 12.9 and the driver is on the 13.0 branch. One critical detail. The model weights are 16 gigabytes per quantization, so make sure you have a separate disk volume with plenty of room. We will be downloading there to keep the system drive untouched. Step 1 is the boring but important part. We pin a specific Python version for this project. I use SDF, which lets you keep different Python versions side by side. We run SDF local Python 3.12.3. Then we create a project-scoped virtual environment with python-mven.venv. From inside that venv, we install the small Python packages we need: Hugging Face Hub for downloads, Pillow, and Matplotlib for the screenshots and charts. One subtle trap is to make sure no stray virtual environment is already active when you create the new one, otherwise your venv picks up the wrong interpreter. Step 2 is building llama.cpp from source. A plain git clone is enough. MTP support is already in the main branch. The configure command is smake-b build-dggml_qda equals on. The critical optimization is -dc make_qda_architectures equals 89. The number 89 is the RTX 4090's native compute capability. Without it, Smake compiles for every GPU generation ever made, and the build can take 25 minutes. With it, you're done in about 7. The build itself is make build-j and the number of cores. You end up with 3 useful binaries: llama-cli for one-shot prompts, llama server for the OpenAI-compatible API, and llama bench for performance testing. Step 3. The weights. We set the environment variable if_home to point at our big data volume. Don't put model files on your system drive. Then we use the newf download command, picking the Q4_K_M quantization. That's a 4-bit version weighing 16.8 gigabytes, which is the sweet spot for a 24 gigabyte GPU. Hugging Face. Xet does the heavy lifting under the hood, parallel chunks, resume on disconnect, so the entire download takes about 3 minutes on a reasonable connection. No real installation is ever this smooth. Here are the 3 speed bumps I hit on the way, and exactly how I got past each one. If you're following along at home, this is the part that will save you the most time. First failure. The moment I typed plain Smake, SDF jumped in with an error saying no preset version of Smake was installed. The root cause is that SDF had a leftover phantom entry free for a Smake plugin, but no actual version pinned. The fastest fix is to bypass AF entirely by calling the system binary /usr/bin/smake. A cleaner alternative is to add a line saying make system to your .toolversions file. Second failure, and this one was alarming. I ran a simple smoke test, expected 16 tokens of output, and the process kept running. 6 minutes later, I checked, and the stout log had grown to 4.5 gigabytes. The flag I used to disable conversational mode, called -no-cmv, was silently ignored in that build, and the CLI looped forever, expecting another chat message. The clean fix is to pipe your prompt to the CLI through standard input instead of using the -p flag. Hitting end of file tells the program to wrap up gracefully. And that wraps it up. We went from a fresh Qwopus box, past a failed llama attempt, all the way to a fully working, 2 times faster Qwopus 3.6 server in about an hour of wall time. All the scripts, the ASCII.doc blog with the full benchmarks, and the raw logs are linked in the description. This presentation was curated and summarized by Omar Hosni. Thanks for watching, and happy hacking!